we might not always be able to find a function f of x with f of n equals an. In other words, when we try that trick where we replace the n by an x and use our laws of limits from Calculus 1, it may not always be possible, especially when we have n factorial in the expression for an. Remember, we also learned the squeeze theorem in Calculus 1, and this could also be applied. If I have three sequences with nth terms an, bn, and cn, and suppose the nth term for A is always less than or equal to the nth term for the B sequence, which is always less than or equal to the nth term for the C sequence. Suppose this is true for any n greater than or equal to 0, then the limit as n goes to infinity of an must be less than or equal to the limit as n goes to infinity of bn, which must be less than or equal to the limit as n goes to infinity of cn. And suppose those outside limits are actually equal, then suppose the limit as n goes to infinity of an equals L, which equals the limit as n goes to infinity of cn, then there's really nowhere else for bn to go than to L, because the limit as n goes to infinity of bn is between L, and there's only one such number. Well, here's an example. We can't actually replace the n by an x and get a nice function here. X factorial, for now, doesn't really make sense. So let's try to find the limit of the sequence 2 to the n over n factorial. And so we're looking for the limit as n goes to infinity of 2 to the n over n factorial. 2 to the n over n factorial is certainly bigger than 0 for all n greater than or equal to 1. So if we can find a sequence C where Cn is always bigger than or equal to 2 to the n over n factorial, and the limit as n goes to infinity of Cn equals 0, then we can use the squeeze theorem to show that the limit as n goes to infinity of 2 to the n over n factorial is 0. How might we find such a thing? Well, this really does require a bit of cleverness. First step would be to write out 2 to the n over n factorial in its expanded form. 2 to the n is 2 times 2 times 2 n times, and n factorial is n by n minus 1, etc., until you get to 1. Now we can pair a 2 with each of these denominators, so this is equal to 2 over 1 times 2 over 2 times 2 over 3, etc., times 2 over n minus 1 times 2 over n. Now the thing about 2 divided by any number bigger than 2 is that that number is less than 1, and when I multiply something by it, it's less than the number itself. So 2 to the n over n factorial is 2 over 1 times 2 over 2 times a lot of things which are less than 1 times 2 over n. So 2 to the n over n factorial is less than or equal to 2 times 1 times 2 over n, because all of those terms in the middle are less than 1. And this is true for all n bigger than or equal to 2. So the limit as n goes to infinity of 2 over 2 to the n is 0. And now we've constructed this sequence Cn, which goes to 0, which bounds our given sequence from above. So we have 0 is less than or equal to 2 to the n over n factorial, which is less than or equal to 2 times 2 over n for all n bigger than or equal to 2, and therefore the limit as n goes to infinity of 2 to the n over n factorial is between the limits of these two sequences, but their limits are equal to 0, so therefore by the squeeze theorem the limit as n goes to infinity of 2 to the n over n factorial is 0. So we can say our sequence converges to 0.